सो मैं विकास अग्रवाल आ गया हूँ आपके सामने B2A सीरीज का नेक्स्ट सेशन लेके. सो आई एम हियर डियर स्टूडेंट्स, माय नेम इज विकास अग्रवाल एंड आई विल बी टेकिंग द नेक्स्ट सेशन ऑफ B2A सीरीज. So this will be the fourth lecture in electrostats, and till now we have covered properties of charge, ways of charging the objects, conduction, induction and Coulomb's law. See, these are the areas that we have covered till now, and today we are going to talk about the concept of electric field. All right, so let's get started already. So dear students, today we are going to talk about what is electric field. Okay, now to understand this, let me ask you a question. Okay, suppose we have a charge, okay, let's say 1 millicoulomb, or any value. 1 millicoulomb is just an example, and we bring another charge near this charge, and then the two start exerting electrostatic force on each other. Okay, hi Anuj. Okay, yeah, okay, you're Krish, fine. I recognize you. Yeah. So we bring another charge near this charge, and the two charge begin to exert force on each other. How did this charge, let's call it by some name, let's call it as A. Okay, it will become easier to talk about it. How did this charge became aware of the existence of another charge? Let's call it as B. Okay, let's call it as B. So how does A came to know that there is a B on which this A has to exert a force, or how does B comes to know about the existence of A? Okay, because they are quite separated, they are distant, and yet they exert force on each other. How do they sense the presence of each other? The answer to this is electric field. Okay, now what exactly is electric field? So we can say that electric field is the space. It is the space surrounding a charged particle in which it can influence another charged particle. Okay, so let me write it here. So we can say that, I hope the red color is visible. Yeah, it is. So electric field electric field, and for now let us assume that we are talking about the electric field of a charged particle. So later on I'll remove this condition, but for now, for starting our discussion, let's say we are talking about electric field of a particle. Okay, of a charged particle rather. Okay, is the space surrounding a charged particle in which it can influence. By influence I mean exert electric forces. Okay, by this I mean it can exert electric force on another charged particle. Okay, so that's how we can define electric field of a particle is the space surrounding a charged particle in which it can influence another charged particle. Okay, let me represent it by drawing a figure. So suppose this is a charged particle, whatever its magnitude is. Okay, so there would be a region around this charge in which if we put another charge, then this charge will exert a force on that charge. So that region will be called as electric field. What is important here is to note that electric field is a region of space. So it's a volume, you can say, like something like that. Okay, so it doesn't have like not exactly a volume. It's not right. It's not appropriate to say that it's a volume. It's more like it doesn't have any unit, like the electric field will not have any unit. Okay, so electric field would be the region surrounding. One may argue or one may think about that maybe it is the distance up to which this charge can influence another charge. No, but we are not talking about that. We are not saying that it is the distance. We are saying it is the region around the charge in which it can influence another charge. Now, if I check Coulomb's law to find out that let's say I want to answer this question, that the electric field of this particular charge, let's call it as Q1 charge. So electric field of this charge extends up to what limits? Okay, extends up to what distance? Okay, so what I will do, I will say that, okay, let me consider this charge to be present here, and let me imagine another charge Q2 at a distance r. By my knowledge of Coulomb's law, I know that it will experience a force given by Q1, Q2, K, Q1, Q2 by R square. And now I'm wondering that for whichever value of R, this force becomes 0. That is the extent, or that is the distance up to which the electric field exists. Okay. All right. So what is your thought, guys? At what value of R does this force become 0? What do you think, guys? When you check this expression and if you try to answer this question, that the distance where this force becomes 0, that is the extent or that is the distance where till where the electric field of Q1 will exist, what will be your answer? Okay, will you say that this distance is infinite? Okay, like when R turns infinity, only then the force becomes 0. And when I'm giving this statement, I'm not even talking about the magnitude of Q1. Like this charge could be a millicoulomb charge, it can be a microcoulomb charge, it can be a nanocoulomb charge, or maybe even smaller than that, and yet I will still be claiming that the electric field of this charge extends up to infinity. Okay. So you can actually note this as a point, as an important point, that electric field of all charged particles, electric field of all charged particles extends up to infinity, irrespective of magnitude and also the polarity. Actually, magnitude and polarity of charge, they don't matter. Okay, so electric field of all charged particles extends up to infinity. What does that mean? Like, am I saying that, let's say a proton, okay, a proton present in this room, the electric field of that proton will extend beyond this room? Mathematically, yes. Beyond this building, will it extend beyond this building in which I am present right now? Yes. Will it extend beyond this city where I am present right now? Mathematically, yes. Okay, so I'm not saying that how strong will it be. Okay, the influence may be pretty weak. It will be pretty weak. Okay, but if the question is whether the influence will be there or not, the answer is yes, it will be there. So irrespective of how small a particle is, its electric field extends up to infinity. All right. So I hope till this we are fine. What do you think, guys? Is that okay, everyone, students? Okay. Now, obviously, the next question to ask ourselves is that if all the particles, if their electric field extends up to infinity, like I have a 1 millicoulomb charge, I have a 1 microcoulomb charge, and both of them have their electric fields extending up to infinity, there is something which looks odd. Like there must be some difference between their electric field. It feels like that. It feels like that there has to be some difference between the electric field of these two particles. And if you feel that way, then you are actually right, guys. The difference lies in the strength of the electric field or the intensity of the electric field. Okay, now what exactly is that? What is strength of electric field? What is, so guys, let's say that let me define strength or let's say intensity. We use both the words, okay? Okay, strength or intensity of electric field. Now, what does that mean? Okay, so suppose, we have a 1 millicoulomb charge, okay, and we have a 1 microcoulomb charge. And if I ask you that whose electric field extends up to a larger distance, we cannot answer this question. Both of their electric field extends up to infinity. But then if I ask you that isn't there any difference in their electric field, I will probably say yes. I will intuitively say yes. Then if I wonder that what can be the difference or how can I highlight that difference, what I can probably say is that let's talk about a point which is equidistant from these two charges. Okay, let's say at the same distance, and that distance can be, let's say, r. Okay, so let's select 2 points at same distance from these two charges, and let's keep a test charge here. Okay, let's keep a test charge here. Okay, so this test charge need to have the same magnitude. Now, in both the cases, whichever particle will feel a larger magnitude of that of force, okay, that particular, for example, this will experience force because of this particle, this will experience force because of this particle. So we know that from Coulomb's law that this particle will experience a larger force. So what we will be declaring is that the electric field strength of this charge at a distance r is more as compared to the electric field strength of this charge at the same distance r. So like this, we are at least in a position to talk about the difference in electric field. Like we can talk about it by talking about the strength and what this strength, like what is the indicator of the strength. We can say that if we keep identical charges at identical distances from the two charges, whichever test charge experiences larger force, we can say that the electric field of the corresponding particle is a stronger one. Or there is a better way actually to talk about this. What we can start saying that okay, let's forget about the parent charge. Okay, let's call these charges as the parent charge, or these are the charges who are producing the electric field. So let's say that this portion is hidden from us. Okay, we don't know about this portion. This entire portion is hidden to us. What we have been told is that in this region of space there is an electric field. We know that there is an electric field. And how do we know that? We keep a test charge here and we find out that on leaving this charge freely, okay, forget about the gravity, there is no gravity. When we leave this charge free, we find that it begins to move in a certain direction. It like the moment you release it, it tries to go in a certain direction, indicating that there is a force acting on it and therefore indicating the presence of an electric field in this region of space. Okay, remember there is no gravity, so you can't imagine that if I leave it, it will drop. It will not, because there is no gravity. Okay, so I leave a test charge. So basically I enter into a room and somebody told me that there may be charges hidden in the room that you don't see. There may be charges outside the room that you don't see, which are producing electric field in the room. Okay, what do? I pull out a test charge. Again, ignore the gravity. I pull out a test charge. I release it at a certain point, and then I try to see whether it stays there or whether it starts moving. If it starts moving, that will indicate to me that there is an electric field there. Okay, because the test charge is experiencing a force. Next, what I will say that okay, I have confirmed that there is an electric field in this region. Now I want to talk about the strength of electric field. Let's say this point is P. I want to talk about electric field strength at this particular point. So how we have defined it is this, that we will check what force is acting on this particle and we'll divide this force by the magnitude of charge that we have kept. Okay, we are keeping a positive test charge. So this ratio will be called as the electric field strength at P, and electric field will be a vector quantity. So this is how we define electric field strength or intensity of electric field. Okay, I'll reiterate. If you suspect that there is an electric field in a region of space, you will keep a positive test charge in that region. If it doesn't experience any force at the point where it is kept, we will say that at that particular point there is no electric field. You can try it at a different point. Again, if you find no force, You can try a third point, fourth point, 100 point. If you're not finding any force anywhere, you can say that, okay, it doesn't seem like there doesn't seem to be an electric field, any electric field present in this region of space. But if you find that there is a, the moment you release the particle, it tends to go into a certain direction, it indicates the presence of a force, and the force per unit, the magnitude of charge that you have kept, is called the electric field strength at that point. Okay, it's a vector quantity. Now, based on this definition and, based on few things that we already know, we can draw a lot of very important conclusions. Okay, for example, what we see here is that electric field is a vector quantity, and let's start with the easiest of conclusions. The first conclusion would be that electric field unit of electric field. Okay, so unit of electric field strength is Newton per Coulomb. Okay, so unit of electric field strength or intensity of electric field is Newton per Coulomb. So that is one thing. The second thing that you can keep in mind is, notice this thing. Okay, notice this point. Okay, direction of electric field at P. Direction of electric field at P is same as the direction of force experienced by positive test charge kept at P. Very important statement, very obvious, very easy, but very important. Okay, so direction of electric field is same as the direction of force experienced by positive test charge kept at P. So what we did, we kept a positive charge here, and in whichever direction the force was acting, we have declared that the electric field is in that direction. Remember, we have declared this. We have assumed that the direction of the electric field is the same as the direction of force experienced by a positive particle kept at P. Let's say we were out of positive particles. We did not have any positive particle. We only had negative particles with us. Okay, so I only had maybe a collection of electrons. I did not have any positive particles, but I wanted to test that whether there is any electric field in this region or not. Okay, so my problem was that I only had negative charges. So I kept a negative charge here. Okay, I hope you do realize that in case a positive charge was kept here and it experienced a force in a certain direction, okay, I'll draw a dotted line. So this was the force that the positive charge was experiencing. Okay, in case if you replace the positive charge with a negative charge, are you able to judge that you will now experience a force in the opposite direction? Are you able to judge that, everyone? Are you able to judge that? Because suppose a positive charge is experiencing a force in that direction, maybe because the positive charge is kept here, maybe because the negative charge is kept here. In both the scenario or in any similar scenario, when you keep a negative charge here, it will experience a force in the opposite direction. So let's come back. Like what was the problem statement? I was out of positive charges. I did not have any positive charge with me. So I tested with a negative charge. I discovered that the force is in this direction. Now, if you ask me that what is the direction of electric field at point P, I will not say it is the same as the direction of force experienced by this particle. No, it's a negative test charge. Okay, but I know that if a negative test charge is experiencing a force in this direction, in case I would have kept a positive charge here, it would have experienced a force in this direction. So what I am trying to highlight is that the direction of EP is same as the direction of force experienced by a positive test charge. I can, also write that direction of EP will be opposite to direction of force experienced by a negative test charge kept at P. Do you agree with this, everyone? Do you agree that in case if you have a negative test charge, you keep it at P, it experiences the force in a certain direction, then we will declare that, okay, the direction of electric field was opposite to this force. I'll give an example on this. Okay, like I'll try to give an example on this. So let's say this is a room, okay, on Earth. This is a room on Earth, which basically means that gravity is present. Okay, we dropped a particle, we released a particle here. Okay, we released a particle which was negatively charged, which had some mass m, and we found that it is floating in air. It is moving around. It is not falling. It is maintaining the same horizontal level, and moving around. Okay. So if you see this happening, will you conclude that there is an electric field in this room? What do you say, guys? Will you conclude that there is an electric field in this room? Because there is something which is balancing out the mg force. There is something which is balancing out the mg force. So that something most likely is electric field, because there is a charge in the particle, so it can experience an electric force. So yes, there is an electric field in this region. Definitely yes. Okay. So if I ask you the question that, if I tell you that particle was found to be floating around. Okay. So this is what I'm telling you. Particle was found to be floating around upon release. Okay, so this is the information I gave you. Now the question that I'm asking, okay, is there an electric field in room? What will you say? What do you say? What do you say? I think we will agree that yes, there is an electric field in this room. Okay, now next question. If I ask you what is the direction of that field? What is the direction of E? What will you say, guys? What is the direction of E? So to answer this question, we can say that we are pretty sure that mg will act vertically downward. So the electric force must act upward. Okay, the electric force has to act upward. And since this is a negative particle, okay, so mg is being balanced by electric force. Mg is downward, so electric force has to be upward. And this is a negative particle, so the force must be opposite to electric field. So I can now conclusively say that the electric field is downward. Okay, so the electric field is definitely downward. Now, going beyond what I explained to you till now, if I also ask you, can you tell, or what is the direction, what is the magnitude of electric field? Can you tell that, guys? Okay, what is the magnitude? We have already talked about direction, so I'm not talking about, so I'm only talking about magnitude now. What is the magnitude of E? Okay, so again, the particle was experiencing mg force in downward direction and F force here, and you see F by Q would be E. Okay, okay. So F can be written as QE, and these two should be equal. So QE should be same as mg, or in other words, E should be same as mg by Q. Okay, I hope we are all clear with this. I hope we are all clear on this. Okay, so till now what we have discussed, that if we want to test the presence of electric field, we keep a positive charge in the at whichever point we want to check, and if that particle experiences a force, then yes, electric field is present. And what is the strength of the electric field? It is force upon charge. If we keep a negative particle, then the negative particle will also experience a force. In whichever direction this negative particle is experiencing a force, we will declare that the electric field is opposite to that direction. Okay, now that was one thing that we did not know about the electric field, and based on the direction of force, we concluded the direction of electric field. Now there is the opposite situation. Okay, we know, okay, what if we know E vector, okay, and we want to find F. So suppose I know that there is an electric field in this direction. Okay, there is an electric field in this direction, magnitude is E, and suppose I keep a negative particle here, and then I ask you that, okay, what is the direction of force on this particle? Okay, will you say that it is this? Because if you say that, that's, you are right. So if we already know the direction of field and then we want to judge the direction of force, for a negative particle it will be opposite to the field, for a positive particle it will be along the field. Okay, getting it? All right, is the calculus in INJSO? So See, Phantom, it's not that calculus will exclusively calculus will be asked. There can be questions based on calculus. Yeah, there can be. Okay. Now, if we are clear on this, let me give you an example. Okay, let me give you a very simple example. So, suppose there is a particle of mass m. Okay, and let's say it has a charge q and it's a positively charged particle. And suppose we projected this particle with a velocity v naught upwards. Okay, and I'm also telling you that in this region of space, there is a downward electric field. There is a downward electric field of strength E. Okay. Now, my first question to you all, do you think that this particle will reach the height of V naught square by 2g? Do you think it will reach the height? You know, this height, I hope you recognize the formula. Okay, I'm recalling it, I'm invoking it from one-dimensional motion under gravity. Okay, so if you throw a particle upwards, okay, it goes till a height of v square by 2g. So in the present case where there is a downward electric field, when that's a positive particle of charge q, okay, do you think it will go till this height or do you think it will go to a lesser height? If your answer is that it will go to a lesser height, then you are absolutely correct. Okay, it will go to a lesser height. So in absence of electric field, if this particle would go to this height, then in the presence of electric field, it will probably go to a lesser height. So we want to know that what is the height till which this particle will go. Let's see how we will do this question. Okay, so this particle is experiencing an mg force downward and it is also experiencing a qe force downward. Okay, so net force is mg plus qe, and if we divide it with mass, we get the acceleration. Okay, let's call it as a. So in the absence of electric field, the acceleration was same as g. Okay, see, if E is 0, then this changes to g. So in the absence of electric field, the acceleration was equal to g, and we were getting the maximum height as v square by 2g. Okay, I can actually interpret it like this: v square upon 2a. Okay, so now the height would be v naught square upon 2 times of this value. So this value is g plus qe by m, and you can see that we are getting a larger value of the denominator, indicating that the height would be lesser as compared to this value. Okay, in the same manner, if I ask you that what will be the time of flight of this particle, okay, what will you say, guys? Time of flight is 2 v naught upon g. Again, g can be replaced by a. Okay, g can be replaced by a because this is not applicable right now. So it will become 2 v naught divided by g plus qe by m. Getting it, everyone? So if there is an electric field present in a region of space, if we know the magnitude is E, then a force QE will act on the particle, and then we have to modify our formula accordingly. Okay, how about we do one more such question? Okay, so let's say this is a wall, this is a block. Okay, this is a block of mass m, this distance is d, and there is no friction here, it is a smooth surface. Okay, and what we did, we applied an electric field E in this direction. Okay, a uniform electric field, that means it is same throughout. Okay, so what happens, like this block was at rest, we applied an electric field, and this block had a charge, it had a charge of plus q on it, so it was a charged block. Okay, are we expecting this block to hit the wall? Yes or no, everyone? Are we expecting this block, okay, to hit the wall? Yes or no? Okay, well, I am certainly expecting, because this block, you know, this block will start experiencing a force QE, which will lead to an acceleration of this much. Okay, and because it's a constant value, we can use u plus at, or we can use v square plus u square plus 2s. So suppose I want to know that what is the speed with which this block will hit the wall. Okay, so we can calculate that speed by putting the values here. We can put 0 here, then acceleration is qe by m, and then s is d. So that will give us the speed with which the block will hit the wall. Okay, if we want to know the time, again we can use s equal to ut plus half at square. There we can make the values, we can substitute the values and we'll get it. Okay, so guys, I hope this idea is clear to you, the idea of electric field. You know, electric field, basically it's a region of space where electric particles, where charged particles experience force. And strength of electric field, how do we define strength? We say that strength of electric field is force per unit charge, force upon charge. You keep a charged particle at a point, it will experience a force. You divide that force by the charged particle, by the magnitude of charge that you have kept, and this ratio is the electric field. If you already know the existence of electric field, you know that this electric field E exists, then every particle which is part of this field, which is present in this field, will experience a force given by Q into E. And then the dynamics, like how the particle will move, etc., those will be governed by what we have learned in Newton's laws of motion. We will just treat as this is an additional force now, and because of this force, the motion is taking place. So students, I'll end it here today. So we have learned the concept of electric field. In next class, we'll talk about the electric field produced by a charged particle, and we'll also talk about the concept of electric flux, which Chaudhary Jay Kadyan is asking. So I'll take it up in the next class, guys. I'll see you next week, everyone. Take care. I hope you enjoyed this session. Watch it again in case if you were not able to understand it. I'm pretty sure that watching it again, you know, at your own comfortable pace, you will be able to grasp each and every idea that I shared today. Take care, students. Bye-bye.